Okay, recall that a solution to an equation with two variables is an ordered pair, right? So it's a x comma y. For example, one solution to the linear equation 2x plus 3y equals 5 could be 1, 1. Because if I were to take x equals 1 and y equals 1 and substitute those values in for x and y, I would get a true equation, right? 2 times 1 plus 3 times 1 does in fact equal 5. And there are, of course, infinitely many ordered pair solutions. And when we plot all such solutions, we get the graph of a line, right? So there was a whole video about this earlier in the course where the idea of plotting all of the solutions is actually our visual way of understanding what it means to be a solution, what it means to satisfy the equation. Okay, but what we're going to do is move everything up a dimension. So if we have now a solution to an equation with 3 variables, x plus y plus z equals 3, well, the solution would be an ordered triple x, y, z. So any 3 numbers that make this equation true would be an ordered triple solution. So here are some examples. 2, 1, 0, that means when x equals 2, y equals 1, and z equals 0, I should get a result of 3, right? So x plus y plus z equals 3. Does the point 2 plus 1 plus 0, does that equal 3? And sure enough, it does. What about 1 plus negative 2 plus 4? Does that give me 3? And yes, of course it does. And finally, negative 3 plus 3 plus 3 also gives me 3. So those 3 are solutions. Can we find another? Well, yeah, pick any 2 numbers you want really for x and y. So say x is 5 and y is negative 7. How could we make this equation true? So again, I'll write the equation x plus y plus z equals 3. So if x is 5, y is negative 7, what would we have to make z equal in order to make this true? Well, so far I've got negative 2 plus z. So negative 2 plus something has to give me 3. So I better make z equal to 5, right? Because 5 plus negative 7 is negative 2 plus 5 gives me 3. Right. So of course there's infinitely many such ordered triple solutions, right? But what happens when we plot these things? Well, remember that when we had just 2 variables, right? So picture our axes, we plotted it. We only had an x value and a y value, and we plotted all these ordered pairs. We'd plot over x up y, and then some other value, over x up some other y value. And we plotted all of them. We got a curve that was a line, because these are linear equations. And it was one-dimensional, right? It was a line. So it was a one-dimensional set of solutions in the two-dimensional plane. But what happens if we move up a dimension? So now what if we have 3 variables that we're plotting and hence 3 sets of axes? So we have our x and y and then also our third variable z. What happens if we plot all these x, y, z's? Well, we would have to go out some number of x and then over some number of y and then up some number of z, right? So we'd be plotting this x, y, z for all of them. So I'd go over some other different number of x, up some different number of y, and up some different number of z. So what's going to happen when I plot all these points is it's going to make a plane, a 2-dimensional plane. So everything goes up 1 dimension. When you plot in a 2-dimensional plane, the solutions of a linear equation, you're going to get a 1-dimensional line. If you plot in 3 dimensions, you're going to get a 2-dimensional plane. Okay, and that sketch is not so good, but let's move over and look at a computer version of a graph. So below is just part of the graph, and we say part because, of course, a plane would extend in all directions, right? A plane is just like a line. Let's go back up here, right? We don't really draw all of the line. We put these little arrows on the end to say like, oh, it would keep extending in both directions. Likewise here, if we tried to draw the plane, we would have everything just sort of shaded in and we can't really see much. So what we're going to do is just take one little clip of it. If we were to sort of cut the 3-dimensional axes into a cube, the part that would be of the solution plane would be this sort of triangle. So the 3 solution points, 3, negative 3, 3, negative 3, 3, 3, and 3, 3, negative 3, those are all plotted right here. We can see them, and then just connected with a plane. Okay, so this is tricky, right? I'm not going to be asking you to graph planes, so this requires technology. And so what we can see is we're already at a disadvantage once we move up into 3 dimensions. We're not going to be solving systems of 3 equations with 3 variables by graphing, right? When we were doing 2 variables and two equations and we were solving, we could either solve by graphing, we could solve by substitution, we could solve by elimination, right? And so what we're going to see is that's not going to be so helpful when we go to 3 dimensions, and really elimination is going to be the game changer. That's going to be the one we're going to stick with. Graphing is going to be too tricky. Substitution is not ideal either, although there is some back substitution happening. But elimination is the key, and we will be using those elementary row operations that we were seeing before. Okay, so in these next few videos, we're going to be sort of formalizing this idea of like how do we take everything that we used to know with 2 dimensions and think about it with 3 dimensions.